So in the last two classes, we have sort of adapted our linear program, our polyhedron, our system of linear inequalities, into systems of linear equations. And we have found out we've done that by adding slack variables to each inequality. And then we've talked about how basic solutions to those systems of equations match up with extreme points to um, our polyhedron, our feasible region. So today we're finally learning exactly how we utilize all of those technologies to solve linear programs. And we're going to do that by doing one example in 2D, in 2 dimensions, and we're going to do a few iterations of that, and ultimately, time permitting, we should solve it to optimality. We should see the whole process. So here's our problem we're going to focus on today. This gray line is the objective function and its gradient, so it is increasing in this direction. And this is x and y. You may already see that the optimal solution looks like that extreme point. No, I don't know off the top of my head what that's. I think it's like 3.64, maybe, something like that. And you can see that because this is a two-dimensional problem. And you might be tempted just to jump straight to that solution and be done with it. But we need to understand how this works, or how this process works in 2 dimensions, because we can visualize everything that goes on. But when we're solving these problems in the real world, they have hundreds or hundreds of thousands of variables, and that the sort of graphical intuition completely evaporates. There's no way to visualize that. So the process is important. I'm presenting it here in 2 dimensions just so that we can see every step as it sort of behaves. So the first thing we're going to do is leverage last lecture and put our LP in standard equality form. So to do this, we add a spare or a slack variable and transform our less than or equal to into an equal sign. And this lets us, or this gives us a system of equations that we can solve for basic solutions, like we've talked about doing. So I've said let x and y be non-basic at the start, so that means that x equals 0 and y equals 0 for now. So we ignore that part and we just solve what remains. S1 equals 1, S2 is 11, S3 equals 4. So our point then is the origin, 0, 0, and S1 corresponds to this sort of distance from our point to the first constraint, S2 is this distance to the yellow constraint, the second constraint, and S3 is sort of the distance to the third constraint. And I keep saying distance, but we need to remember that these metrics are not identical between constraints. So the true distance to this yellow line, the Euclidean distance, is probably something more like 5.5, but we have an 11 here, so it's not quite exactly Euclidean traditional idea of distance. So moving on, that's a solution, x0, 0, and it has an objective value of 0. So what do? We want to change our solution from the origin. And notice that the origin, why is it disappearing on this page? This page is cursed. Excuse me? For what, though? Oh, okay. Sure. So we want to change our solution. We want to look at a different extreme point and sort of compare the objective function value at that point. And we're going to do that by changing the basis. Notice that 0, 0, we had a basis, and that 0, 0 is an extreme point because we have non-negativity constraints. So it is the sort of intersection of two non-negativity constraints. So I guess the question is, we have two non-basic variables. If we want to change the basis, that just means we are going to swap out one of the basic variables for one of the non-basic variables. So we have the basis is S1, S2, and S3 because they take positive values, and the non-basic variables are x and y. So x and y equals 0. We want to, improving either of them, notice, or increasing either of them will actually increase the objective function value. So we want to increase one of those. Looks like x is a little more efficient. It has a higher coefficient, so it's going to increase the objective faster, in a sense. So let's pick that one. Let's increase x. In other words, we're going to let y remain 0. And we're going to think about what happens when we increase x. So the first constraint tells us x minus x1 equals 1, 2x plus s2 equals 11. And the third constraint doesn't have an x in it anywhere, so we could ignore that one. Um, so how far can we improve x before we breach outside of the feasible region? So if we look at our graph, we're just increasing x, so we're just coming across this line. But we're gonna kick out of our feasible region right there. So we can see that graphically, but how do we determine that algebraically? Well, x minus s1 equals 1. If we increase x to, say, 1, then we have, oh, correct, yeah. So if x equals 1, then we have 1 minus s1 equals 1, which tells us that s1 equals 0. At x equals 0.5, we get that s1 equals 0.5. Nope, this should be a plus. Yep. So increasing x decreases s1 proportionally, and then ultimately to 0. If we were to increase x past 1, say 1.5, or actually, for my sake, 2 plus s1 equals 1, we would find that s1 equals negative 1, which breaches our non-negativity of s1. So that would be infeasible. So the first constraint tells us that s1, or x, can only go as far as 1. So we have x less than or equal to 1 as a sort of first idea. Our second constraint, let's just go ahead and set s2 equal to 0, because that's what we want to know. When does that happen? 2x equals 11 implies that x equals 11 over 2 is 5.5. So that's much bigger than 1. So if we were to plug that into the first constraint, we would get an infeasibility. So we're just going to use the first one we have, x1, or x equals 1, the smaller of the two sort of possible values. And this is nice in a way because if x equals 1, then s1 equals 0, and we can put s1 in our non-basic variables sort of set. So our basis remains the same size. We're going to swap x into the basis and s1 out of the basis. So then we're just going to solve for, so we have x equals 1, y equals 0, s1 equals 0 from up here. S2 equals 11 minus 2 times x is 9. And S3 didn't have x in it at all, so S3 stays 4. And this is our new solution. And that has a objective function value of 1.5 times x is 1. Is 1.5. So we've improved our solution. We found an extreme point that has a better objective function value, which is good. That's what we want to do. Our next question, though, okay, well, let me recap what we've done. Each extreme point, remember I've said this several times at this point, each extreme point corresponds to a distinct basis of the SEF LP, of the LP in its standard equality form. So at each iteration of the simplex algorithm, which, by the way, is the name of the process we're doing today, we want to explore a new extreme point, i.e. a new basis. So to do that, we exchange one basic variable for one non-basic variable, and then identify the corresponding solution. So what we did last time is we exchanged x for s1 in the basis, or s1 for x, I suppose. Now we're at sort of a sticky point, because this model doesn't tell us what to improve next. Right? We could try to increase y, but it's not clear exactly when increasing y would become infeasible. Maybe it is clear on this two-dimensional problem, but again, we could have hundreds of thousands of dimensions, which would make any sort of intuition nigh impossible. So instead, we're going to put the LP in what's called the canonical form for our new basis. So I'm just going to remind us that our basis is currently x, s2, and s3. So we want to re-express our current LP in the what's known as the canonical form for our current basis. So the first thing we're going to do is we're going to identify the columns of our basis, these three, and we're going to merge them together into one matrix, call it AB. 1, 2, 0. Right. If you remember from our basic solution sort of discussions, and well, from other things, we can express this whole thing as a matrix notation, and better yet, we can, well, maybe not better, but we can expand that that constraint into this. Which is our basic variables plus our non-basic variables equals b. So that's just what we've done here. We've pulled out a sub b, and then we're going to find the inverse. And you may remember that Since A of B is a basis, by the definition of a basis is that all of the columns are linearly independent, and the matrix is square, so it's invertible. And I'm just going to go ahead and reveal the inverse. Yeah. And then we're going to do some matrix algebra. It's going to get a little bit convoluted, so be prepared. First thing is to multiply our our B column. So that's our little B vector times this new A inverse. One negative 2 0 0 1 0 1 times 1 11 4, and that equals 1 times 1 is 1. Negative 2 times 1 plus 11 is 9, and 1 times 4 is 4. And that looks like a 6 in there. That should be a 0. So we'll notice that this is our basic solution from the last screen. We had a 1, a 9, and a 4 in the same sort of order. Here we have 1, 9, and 4. That's not a coincidence. That is our basic solution. So then we want to change the inside of the constraints. So we're going to do that by AB inverse times A times X, which is of course the same as AB inverse AB XB plus AB inverse AN XN, which is XB AB inverse AN XN. So the only matrix multiplication we need to do is this second term. So this AN, this non-basic matrix, is just the other columns that we hadn't picked before. Times xn, which is xb plus negative 2 plus 1. Nope. Is that the right? Nope. That should not be a 1. That is a 0. Yes. So that is negative 2, 1. Negative 2 times negative 2 is 4, plus 1 is 5. have 2 times 1, 1 times 1, and 0 times 1 times xn. Xn being our non-basic variables. Remember, we are here currently at 1, 0. What we're trying to do is re-express our LP so that our directions, the directions we could move, are sort of more obvious from the LP itself rather than from the plot of the feasible region. And maybe we'll see that in a second. So, if we combine all of that together, we get this new feasible region. We'll see that it's xb, so our basis, x, 2, and 3, are added without any coefficients. And our non-basic matrix is right here, this matrix. So the only thing we haven't fixed yet is the sort of the objective function. And the problem is that x is already in the basis. So we can't increase it directly. If we just increase x, remember that we're going to shoot off into infeasibility. And remember that our process involves jumping from basis to basis, and we can't sort of change our basis without increasing a variable other than x, one of our non-basic variables. So our non-basics at the moment are y and s1. So what we want to do is find out whether or not increasing any of those actually increases our objective. So let's think about what happens if we increase y by 1. I.e. we put it, well, okay, while staying feasible, while maintaining feasibility. So we are here at 0 to 1. And what we want to do, when I say increase y, we could just shoot up off that direction, increase y itself, and not worry about anything but when we hit this edge S3. we could do that, but that would land us at a non-extreme point. And we don't want to bother looking at non-extreme points, because the optimal solution, if it exists, will be at an extreme point. So instead, we want to ride this constraint up this direction to this point. Spoilers. So how do we find out? So I guess the question is, how does that affect our objective function value? That's what we want to know. So we look at this blue constraint is our first constraint. So x minus 2y equals 1. We're going to, for now, ignore s1 because we're staying on that constraint, which s1 is the slack variable for. So s1 is not going to increase past 0. So ignore s1 at the moment. And in fact, let's change this a little bit because we already know x is 1. And we want to know how x will change if we increase y from 0 to 1. Gives us actually a delta x of 1 plus 2 minus 1 is 2. So increasing y by 1 increases x by 2, which makes our objective, so let me just write that. Y by 1 increases x by 2 and increases the objective value by 1 times y, or 1 times 1, because our objective function has a 1y in it already, plus 1.5 times delta x, which is 1 plus 1.5 times 2, which is 4. So increasing y by 1 increases the objective by 4. So we ought to have a new objective of maximize 4y. And then doing the same analysis on s will show us that increasing s by 1 decreases x by 1. Which is moving this direction back the way we came. So it's no surprise that that sort of decreases the objective function by 1.5 s1. And further, it's good practice to include a constant for the objective function at the current basis, which was 1.5, because we have x equal to 1. So this is going to be, let me raise that up. our new objective to go with our new LP. So before we reveal that, we talk about what we just did sort of in general. This is a horrific nightmare of linear algebra spaghetti. It's just everywhere. It's hard to look at. But hopefully I can break it down to make it a little more sensible. So if we have an LP that's in standard equality form, and a basis B, the canonical form of that LP for that basis is given by this nightmare right here. So this is the format that the book gives it in. They have a slightly different notation, but I've expanded it out because I think it's more legible. And then down here is the format that the graduate student book that I have gives it in. You'll notice that we have the same term here, and that these terms are sort of similar. The only difference between these two is that we've expanded out this A into AN plus AB, and then shuffled things around and canceled out some of our basic components, which is the same thing I've done in the constraint. Just pulled out the XB like we did here. Previous slide. So what? So this term, this A inverse B times B, is the current basic solution. And you'll notice that that term is also over here. And you'll remember when I pointed out that A inverse B times B was lined up with our basic solution that we had computed. So then, if we multiply that by C, which is our objective coefficient, that gives us our current objective value. Which you'll remember we included in our new objective function. Then Cn is the objective coefficients for our non-basic variables. So that would be improvement from non-basics. Whereas this term is the same as this whole process. So that is the improvement ooh, my spelling is impeccable up here. Improve mint. Yeah, no, my spelling is terrible, so if that annoys you, sorry. Improvement from indirectly changing the basic variables. And we need the minus because that, for whatever reason, turns out to be a negative value. So then this is just our basic variables plus some new sort of constraints. So we can think about this term as looking sort of like our standard equality form. So this looks similar to SEF or XB is the slack. Remember our SEF standard equality form looked like this. So some matrix times some variables plus some more variables equaled a vector. So in that sort of vein, we have what looks like a whole new LP, sort of. We have a new objective function, which we computed a couple slides ago. And we have our new feasible region, which we computed the slide prior to that. So this looks kind of like a whole new LP. And if we plot our non-basic variables, again, this is y, and this is S1 rather than x. We have a region that looks different, but still mirrors our original region and is in fact sort of equivalent in a way. So from this sort of mindset, x, S2, and S3 are slack variables. This is the same 5-dimensional system of equations projected onto a different 2-dimensional plane. So if you remember when we talked about the standard equality form of vectors, I mentioned that a polyhedron could be expressed as the projection of a higher dimensional system of linear equations. And all I've done different here from the last few slides is project this onto S1 instead of onto X. Just to give us some idea of that we can interpret these LPs in a variety of different ways, but they're all sort of equivalent. All of those interpretations. So, I guess, what do we do from here? Well, it's pretty clear that improving y, or increasing y, will increase our objective function value by quite a bit, it would seem. So all we're going to do is repeat the process. So here we're back in our xy space because it makes some sense to me, and we want to track our movements. So we started at 0, 0. We moved to 1, 0. And now we are going to increase y. And so that, right. So what we need to do to refresh our memories, we're going to put y in the basis. So y enters the basis. So 1 of x S2 or S3 will need to leave. The basis. So the question is, which one of those can leave and the problem, and let the problem remain feasible, or the basis remain feasible? Yeah, so let's think about that. Here we have a minus sign, so increasing y will just increase x. Also, we're forgetting about S1 for now. S1 remains 0, so we can ignore that part for now. So increasing y increases x, and it doesn't impose any restriction on feasibility. So the first constraint y e increases x indefinitely. And we'll notice that that's because there's a negative sign on that coefficient. Two gives us that y equals 9 over 5. If we set S2 to 0, we get 9 over 5, which is, I forgot to compute this numerically, 1.8. And, excuse me, the third constraint gives us, if we set S3 to 0, y equals 4. Notice that if we plug y equals 4 into the second constraint, we'll get 5 times 4 is 20, plus a positive number equals 9, which is not true. So this would be, this would make S2 negative. Which would be infeasible. So we're going to go with this, which means that S1 leaves the basis. So our new basis is not S1, S2. S2 leaves the basis. X, Y, and S3. So last time what we did was we solved for the solution first. Well, I guess we can do that again. Yeah, let's do that again. So, you know what? I'm going to do it instead by inverting the basis matrix. So our AB, I'm going to move up here, is 1, 0, 0. The first column has to do with X. X is our first element in the basis. Negative 2, 5, 1 is our Y column. And our S3 is 0, 0, 1. Sort of the nice thing about this process, well, one of the nice things about this process is that at every iteration we're only changing one column of AB, so we have a relatively easy to invert matrix. This should be 1, 0, 0, 0, 0, 1, 1/5 in the middle here, minus 1/5, and 2/5. So then remember that AB inverse B is our basic solution. Times 1, 9, 4, which is 1 plus 9 times 2/5, and then 9/5, and negative 9/5 plus 4, which I happen to have is 23 fifths, 9 fifths, and 11 fifths. So our basic solution is then x equals 23 over 5, y is 9 over 5, s1 is not in the basis, so it's 0, s2 is not in the basis, it's 0, and s3 is 11 over 5. Let me get the is 1.8, and x 27 divided by 5 is 5.4. So that is 5.4. Is that right? It's 23. It's 23 divided by 5 is actually 4.6. So 4.6 1.8 is our new extreme point. So we've just traveled up this way. And perhaps the best part is that we don't need to bother increasing or plugging this into the objective. We can just plug in our increase in y into our objective. So 4 times 1.8 plus 1.5 is 8.7 is our new objective function value. So we've improved it quite a bit. Now there's one more step we can do. I'm just going to ignore and not do all of the matrix algebra again, because we'll be developing a process to do that all in a better sort of single step later, specifically next lecture. So I'm not going to dwell on it too much. Instead, this is the canonical form for our new basis. X, Y, S3. You'll see that we have sort of an identity matrix for our basic variables. They're only in one constraint each, and they only have a coefficient of 1. So if we looked at A, that would be 1, 0, 0, 1, 0, some stuff for S1 and S2, 0, 0, 1. So their columns correspond to columns of an identity matrix, which will be important for us in tomorrow's lecture. So what do we do here? Well, is that right? want to increase S2. I get the feeling that those coefficients are not quite right. In the objective function. Give me a moment. So increasing x1 increases x, or decreases x by 1, increases y by 5/2, so 5/2 times 5/2 minus 1.5 times 1, so 5/2. Yeah. This is a plus, and this is a minus. So what we want to do is we want to, S1 is a positive, has a positive coefficient. Excuse me, I feel a sneeze coming on. No, false alarm. Okay. So S1 has a positive coefficient, so increasing S1 will now increase the objective function value. So we're going to tuck S1 into the basis somewhere. Enters the basis. So we're going to ignore S2 for the moment. Increasing S1 decreases x, so it can only go to x equals 0, which is going to give us S1 is 23 over 5 divided by 1 over 5 is times 5 is 23. Increasing S1 increases y, so we can do that indefinitely without putting y in the negative, so we don't care about the second constraint. It doesn't impose any sort of cap on S1. The third constraint gives us S1 equals 11 over 5 divided by 2/5 times 5/2, which is 11 over 2 is 5.5. So we're going to pick S1. Yeah. Pick S1, and we're going to knock out S3. So our new basis is x, y, and S1. Now, we've moved from here to here, up to here, to this extreme point, and now we're increasing S1, which means that we're moving away from the blue constraint, because that's our first constraint. which means that we're following this edge up here, and we're going to get to this extreme point. At least we should, if I did my math right. And I'm not going to belabor this by finding any new, or by doing any more matrix algebra. So I'm just going to skip ahead to the next slide. I'm going to copy this. No, that's not what I wanted. Copy this. Paste it on this slide. So this is the canonical form of our new and final basis. This is the basis x, y, s1. And we'll notice that our objective function rho only has negative coefficients. So if we increase either of our non-basic variables, we are decreasing the objective function value, which we don't want to do because we're maximizing. Which means that we're done. We've solved the problem. Everyone, round of applause for following along. That's a struggle. That's a lot of things floating around to happen. Lots of steps. But that is the gist of the simplex algorithm. And tomorrow, what we're going to do... Well, so first, this is hard for us to wrap our heads around a little bit. There's a lot of matrices floating around, and if you forget one little piece, suddenly you're in hot water because none of the rest of your iterations line up. It's hard to do by hand. A computer can do this just fine. So this is how a computer visualizes this sort of problem, probably just with the matrices. But what we're going to do tomorrow, and in your reading tonight, is put our LPs in what's called a tableau, which has all of the relevant information sort of in one compact table that we can do instead of matrix multiplication on, and instead of remembering all of those convoluted matrix algebra equations, we can just do some row operations. In fact, we'll just be doing Gauss-Jordan elimination. And that's going to be sort of a game changer for letting us do this. So, yeah. So just to reiterate the sort of step-by-step process of this, and point out what's important for us to remember going forward. So we're going to pick the best non-basic variable. The best in this case meaning most positive in objective function. And then we're going to pick the most constraining basic variable. And then and then 3 swap those two. And then 4 find a new canonical form. And then repeat. Repeat until there's no more positive value in the objective function. That's the simplex algorithm. And it's hard. There's a lot of pieces to remember, lots of things floating around, but hopefully tomorrow we will make that a little easier, a little less to remember. So if you're curious, we can see that from our current canonical form that we are at the point 7 halves 4, and it has the objective function value of 9 and a quarter. So this had an objective function of 0, this was 1.5, this was 8.7. And I'm sorry that this lecture was kind of just me rambling. There's a lot to cover here, but it's 10:45 now, and I am just in time, done with my content. So I'm going to stick around if anyone wants me to go over anything else, but you guys are free to go.